We are now going to discuss the topic of the evolution of computers, chapter 2. If you've read the history of computers, you've probably read about people like Charles Babbage, way back in the 1800s, who discovered the notion of a computer. He actually had the entire architecture of the computer laid out on paper at least. But unfortunately, at that point of time, the technology didn't support him. He could not make a computer and convert his idea into reality. However, throughout the early 1900s, if you've seen, computers as a concept have rapidly evolved. And there was a time when the first computer, for example, the ENIAC and various other devices which were created, were huge computers filling up an entire room, for example, an entire hall. They were made out of what you call as valves, electrical valves, and complex circuits physically connected to each other to make the computer do very fundamental things like add, etc. And it's been over the last 50 to 60 years that you've seen rapid pace of evolution of computers from where it was to tremendous micro miniaturization of the computer. Now to say that we have a complete computer on a single chip, which is possible. You have nanotechnology, for example, which has come up where you can actually embed a computer inside your body in a small device of that size. Now that's been the evolution. So very quickly to walk through the evolution stages in terms of hardware, for example, how it has evolved. So if you see the first generation of computers, as I mentioned, was huge wall-based computers, physically connected. Then came the era of solid-state electronics. So you had solid-state devices, silicon-based devices. They were still single devices. They were separate devices which still had to be connected, and the computers were therefore still very large at that point of time. Then came generation 3, which is integrated circuits. So multiple aspects of your circuits were compressed onto a single circuit board, and you could pack millions of transistors and millions of discrete devices onto a single circuit. That reduced the size tremendously. It reduced the power consumption. It improved the reliability of devices significantly, and the speed, of course. Now, of course, what you have is very large scale integration. So when you talk of microprocessor, a microprocessor actually embeds millions of devices within itself, and that gives you a complete CPU, a complete processor on a single chip. Now, the concept of a microprocessor is that of a CPU which does everything. It's a complete computer. It is programmable, and it can do all the basic operations such as the logic, the movement of data, the control of other devices and such things. So if you've seen today, for example, even your mobile phone carries a CPU of a kind. That's a microprocessor chip which it has. Many of the automation systems that you have, controlling machines, for example, robots, for example, they use a lot of microprocessor chips. And microprocessors, therefore, have become fundamental to any operation, whether in the business side or the automation side of business. Now, how do microprocessors evolve? How have they evolved over time? And you'll see, for example, from the earliest in the 70s, you had something known as an 8-bit processor, which was the 8080, one of the first earliest processors that was actively used to produce a small PC at that time. And from there you had gradually 16-bit processors and 32-bit processors in the late 80s, and then throughout the 90s and 2000s now we work on 64-bit processors. What does this imply? Word size of 64 bits implies that 64 bits are handled at the same time. So tremendous amount of raw processing power. Complex and large data can be handled at the same time. Complex calculations can be done, and more importantly, you can access a huge amount of memory, because memory, each location of the memory has an address, and you need to be able to directly address so many addresses in memory. So 2 raised to 64 is the amount of memory that a processor of this kind can potentially directly address. Clock is the other important evolution that has taken place, and clock speeds have increased from some minimal numbers which I don't even remember now to today what we talk about 2 gigabits and 3 gigabits clock speed. So 2 gigabits per second or megahertz or gigahertz are the terms used when you talk about clock speeds. What is a clock? Clock is actually a piezoelectric device, if you look, or an electronic device which sends a timing signal. So everything that happens in a CPU, for example, two numbers are added once you give a signal. A data is moved once you give a signal. So everything that happens in a processor and indeed in the computer is on the basis of this signal which goes, and the speed of the signal decides how fast all these actions would take place. So this is very typical of analogy which I have given, that if there's a column of people doing a march past, there's a drum beat which synchronizes their actions, and this is exactly what a clock does in terms of synchronizing actions within a computer. Obviously there's a problem here. If you keep drumming fast and fast, the people walking in synchronization lose their synchronization. So somebody is lifting his left leg and somebody is lifting his right leg because the drum is just beating too fast and they are not able to keep speed with it. It implies therefore that every processor is designed to work at a certain clock rate, and that's the maximum rated speed at which the CPU can work. Of course, there are CPUs which can work on two different speeds, but they are again designed to work on the higher speed and the lower speed, and that's a design choice that you make. So when you select a CPU, you are trying to select an appropriate clock rate which gives you a good performance for the CPU. Software is the other thing that has evolved in computers, and software is again with respect to two things. One is the basic operating system itself. You've seen a huge amount of evolution, and second, the application side of the software, which is again transformed over the years. We'll look at both sides. So as far as operating systems goes, there used to be a time when people used to actually give instructions manually to a microprocessor or to a computer by actually connecting the walls, for example. Nowadays it's just not doable, it's not practicable to do these kind of things, because if you want to do complex processing on the fly and quickly, you can't be wasting time connecting devices and such things. So therefore the notion of software has evolved, particularly after the third and fourth generation computers, where software became a distinct component of the computer itself. So there's a hardware and there's a software which makes that hardware more usable, and these are two distinct components now. The operating system is something which has evolved over time, and earlier days there used to be proprietary operating systems. So each computer manufacturer would write his own operating system to suit the CPU which he has designed. So for example, IBM used to have its own operating systems, and Digital, which was another very well-known company at that time, had the VAX operating system, for example. They were very popular throughout the 70s and 80s, and they served their purpose. However, the problem was that these two machines could not speak to each other because the operating systems were not designed in a manner where they could share information and exchange information. The protocols were different. Result of which the world realized soon that there is a need for a standardized operating system, and that's how Unix evolved. And Unix became an instant success, and people liked it because of the sheer facility of communicating across devices and across machines very easily. That's known as portability. So if I write a piece of software, it will work on this computer, but it will also work on some other computer as long as they all use Unix. Along with Unix, particularly on the small machines that in those days, so for example, Apple developed a computer long back which was a small in the early 80s, and that's like a desktop machine, and they needed an operating system, so they created what's known as the CP/M operating system. And then came Microsoft, and Bill Gates developed, as you famously know, the MS-DOS to make the PC, the IBM PC, workable, and IBM bought that operating system, and the rest is history, so to speak. So Microsoft became big because the number of PCs that today use the Microsoft operating system is enormous. In fact, it claims almost 85% market share in terms of operating system, the smaller ones being Linux and other operating systems which have come up in the recent times. Various versions of DOS have evolved as we have gone along, and the major significant evolutionary step that happened was to move from a character format to a graphical format. So the MS-DOS operating system, particularly when it became the Windows operating system for the first time, the entire concept of graphical user interface came up, and that revolutionized the way we interact with computers today. And it's a feature of the operating system which enables you to do that. So you have icons and you click on the icons and make actions possible, rather than having to type complex and cumbersome commands as you would do in the Unix platform, for example. So there's a growing family of operating systems. On one side you have the open operating systems called the Linux and Unix variety, and on the other side you have the Microsoft variety of operating systems which have continuously evolved. So you had Microsoft 98 and 93, and you have had 2000 and 2007, and now you have the latest operating system from Microsoft as well. The interesting part about Linux operating system was basically a response to the fact that Microsoft started becoming dominant, and then you had a problem in terms of depending too much on one vendor for supply of the operating system. So the world realized that soon enough, and a variant of Unix which worked for PCs and for laptops and for various other devices known as Linux came up. So this is what you call as freeware, or not exactly free actually. You need to buy the license, but you probably get it more at a much cheaper rate compared to what you get a branded operating system like Microsoft. Languages is the other thing where evolution has happened. So we have talked about evolution in terms of hardware, evolution in terms of operating systems, evolution now in terms of application software, which is essentially because of languages. So in the good old days we had machine code, and even now we have machine code at the heart of it, because the machine only understands zero voltage of -5 volts. It understands 0 or a 1, that's it. It's the binary form of logic which the machine works on. But there is something which is very cumbersome to code. So in the good old days, people actually, the software engineers took the trouble to do that coding, but now it's just not convenient to do so. Therefore came a set of languages known as the assembly language. So every microprocessor has an assembly language associated with it. So if I want to program a microprocessor, I use certain instructions for which the microprocessor has been designed, and they are semi-English, they are short form notations. For example, if you would write a command like LDA, 10, it indicates load, and LD is a short form of the word load. Load the value of 10 into a register called A, which is a memory location called A. Now these kind of instructions made it a little more easier for engineers to quickly code and also understand what they have written, and these are known as assembly languages. However, assembly languages vary with the processor, so every processor will have slight variation in the language format itself. But the other important thing is you need to convert from this near English like into a machine code, and that converter is known as an assembler. An assembler is a program which you buy, and you write the language code in English and you get it converted into machine code using the assembler. This still is very technical, and I think it's suitable for technical engineers who are writing automation software and such things, machine automation and such things. But what about people like us who are interested in business data processing? We can't write in languages such as these. So evolved languages like COBOL, for example, these are known as third generation languages. They are near English like, they're almost English actually. And if you read a COBOL program, everything looks English. So you have commands like move and commands like add and commands like calculate or multiply. So it becomes so easy for people to understand. So bulk of the languages today are of a third generation variety, which have of course got phased out over the last decade or so, but they were extremely popular, particularly from the standpoint of ease of writing it and debugging it and testing the program that you've written. Third generation languages are typically known as procedure oriented languages because you need to describe the exact procedure that you want to program in the system. So for example, if I'm doing a payroll processing and I write a COBOL program, what I'm essentially trying to say is, please open the file called the payroll file, salary file, pick up the basic salary, additional allowances, etc., move it into memory. Then I'm saying, please calculate the total salary payable this month for this person. Then move the data back into the printer and print it. Having printed it, move to the next person, pick up the data and repeat it. So what I'm describing is a looped process of taking one employee's salary at a time, calculating it, printing it, and then moving to the next one. Now the minute you write the entire procedure like this, the language supports or provides commands to enable you to do this looping, for example, or to do branching. And these are therefore examples of procedure oriented languages. A lot of procedure has to be described when you write a program like this. Again, because these are near English like, the machine still understands machine code. You still need a converter. These are known as compilers. So typically you write a program in COBOL, put it through a compiler. The compiler indicates all the errors. You remove all the errors. So now when you compile, there are 0 errors. You get an executable code. As you know, in many times you on the file you see .exe or .com. These are executable programs. And once you generate an executable program, you can run it. Now, third generation languages are passe. I mean, they are the last whole decade has been more of fourth generation languages, interactive languages, languages which allow you to on the fly type a command and expect a result. Now, these are languages, for example, one very popular one is the structured query language or the SQL, where you can actually indicate, a simple command in SQL could sound like select name and salary from the employee master file where salary exceeds 1 lakh rupees. So what you are telling the computer is, please get me a list of people, their names and the salaries from the employee master wherever the salary exceeds 1 lakh. So you are only describing what you want. You're not telling it how to get it. You're not describing the procedure to get it. You don't care where it is stored. It's the database system which knows where the data is being stored. So therefore, these are languages which are non-procedure oriented. They are simple for end users to type in. They are specification oriented. They only specify what the person wants, and the logic of how to get it is something which the software knows. Now, these are therefore known as fourth generation languages. Above that, there's an entire generation of languages which is evolving, which are fifth generation languages, which is what are known as natural language processing. So what if a computer can understand verbal commands that I give? What if the computer can understand gesture based commands that I give? So if I can do hand gestures or mouth gestures, or I can encode, let's say, a whistle, for example, and it understands it. Now, various forms of natural interactions which humans are used to are being converted into language forms for computers. So the intelligence of computers is growing, and if you come to robotics, for example, I would expect a robot to understand what I speak to him, and therefore these languages have evolved. But you find a whole lot of them in practical consumer products today, for example. Even a computer today can take voice commands. A mobile phone can take voice commands. You can have games, for example, like Wii, for example, where you can do gestures and it can respond to it, so on and so forth. So this has been the evolution of languages in general. But more importantly is the impact. And thanks to the evolution of languages, it's made it possible for us to develop softwares which make the computer usable for a variety of applications. So you've seen in healthcare, you've seen them in public life, e-governance, for example, you've seen it in manufacturing, you see a lot of applications in airlines and ticketing, and then you see a lot of applications for any other service organization like banking and insurance, making our life so much more easy. So languages make a computer very versatile in terms of applications, and that's been one of the biggest impacts. Throughout the 90s, there's been one important trend which cannot escape our minds, and that's the evolution of the internet. So starting from mid 90s, when internet really came mainstream, from a small scientific community, it was brought to the mainstream. You suddenly found a spurt of languages evolved which enabled us to develop websites, web interactions, web portals, and complete e-commerce eventually is what we are seeing today. So you go to, for example, doing a railway booking, and you have the IRCTC site, and you go there, you can check the trains available, you click on them, and you get information about the availability of tickets, and you can actually book, and more importantly, you can even do the payment transaction on the spot. Now all this kind of application is thanks to all the web technologies that have evolved in a wide variety of languages such as ASP and Java and so on and so forth, which have made it possible for us to develop complex web-based interactions, making it possible for the entire world to connect on a global level. Now these languages have changed the face of the way we do business and live our life in general. And with that we come to the end of chapter 2, which is the evolution of computers. Thank you for being with us.